The purpose of this video is to show you how you'll do calculations for your mass and volume measurements lab. I want to point out that the data I'm using here is not the data you'll use in your lab report, as I've got clearly here with this watermark on both of these bits of data. So do not use this data in your lab report. There is a separate document in the lab folder that has your data. Do not use this data. I'll keep on saying that throughout this video because I don't want anybody to use this data. Alright, so let's start off with the first part, weighing two blocks. You'll notice that these are the masses of two blocks. They're measured to 2 decimal places, as we customarily do when we're using a triple beam balance. You'll need to watch the lab video or read the lab manual to see how we actually take these measurements. The mass of both blocks here is the mass of both of these blocks together. But here you're looking to calculate the combined mass of both of those blocks, and the way we'll do that, of course, will be to take 78.90 grams and add 45.25 grams, and then we come up with our result. In the calculator, it's going to come up to be 124.15 grams. And you'll notice that when we're doing addition, what we do is we look at the number of places past the decimal point. And here we've got 2 decimal places. And here we've got 2 decimal places as well. And here in our answer, we expect to see 2 decimal places too. So this would be the correct answer for this specific calculation. In the next one, we've got the volume of water in a graduated cylinder. They're both measured to 1 decimal place. So we would get the measurement of the test tube by subtracting these two values, 92.0 minus 63.0, and that's going to be 29.0 mils. Now, as far as the significant figures go, again, it's 1 place past the decimal, and 1 place past the decimal again, and 1 place past the decimal in our answer. And this is because we're using subtraction, and here we were using addition. So it's the same rule there. We're just looking for places past the decimal to determine how many significant figures we're going to end up with in our answer. Alright, so let's take a look at the next part here, and we're looking for the number of drops in 1 mil. And the way we're going to do that is we're going to take the 45 drops and divide that by 3.0 mils. Now this is division, and what we're looking for is a number of significant figures. So this would be 2 significant figures here, and this will be 2 significant figures as well. Remember that the 0 will be significant because there's a decimal point in the number, so it's 3.0. So our answer here is going to be 2 significant figures, which is going to come out to be 15 drops per mil. Okay, I'll clear this out, and we will move on to the next page here. And here we're looking for the volume of a block, and we have the length and the width and the height. These have been measured to 2 decimal places in accordance with how we use a ruler. You can again get more information from watching the lab video or reading your lab manual. So the way we're going to get the volume here will be length times width times height. So it'd be 8.50 centimeters times 9.40 centimeters times 3.30 centimeters. In our calculator, it's going to come out to be 263.67 cubic centimeters. Now that's what the calculator says. Now the unit there is cm cubed because it's cm times cm times cm, so centimeters cubed. But if you look at the number of significant figures here, they all have 3 significant figures. Each one of these has 3 significant figures. That 0 is also significant because there's a decimal point in the number here. So we need something here at the end that is also going to have 3 significant figures. So that needs to be rounded to 3 significant figures, and that's going to become 264 cubic centimeters, and that will be the answer that we're going to use there. And again, this answer has 3 significant figures. This one had 5. This next one is fairly simple as well. This is the delivered, the volume delivered from a burette, so it would be 11.50 mils minus 2.00 mils. And again, we're using the number of places past the decimal, so 2 decimal places. Again, 2 decimal places. And our answer is going to come up to be 2 decimal places as well. So it'd be 9.50 mils. And that has 2 decimal places. The last one here is the temperature, and you can see that's measured to 1 decimal place. And that's 20.1 degrees Celsius. If we convert it to Fahrenheit in our calculator, it comes out to be 68.18 degrees Fahrenheit. If we look at the number of significant figures here, we're going to be looking at 20.1 degrees Celsius. So that's going to be 1 place past the decimal, and that means we need 1 place past the decimal here. So we will go 68.2 degrees Fahrenheit. Now I know initially you might be looking at this and you might be saying, well, isn't this a multiplication division? Well, no, it actually isn't, because the equation that we're using to get that is this one here. I'm going to just get rid of some of this other stuff here. Is this equation here, 5f minus 9c equals 160. And these are all counting numbers. So that 5f there is actually not 5f. It's really f plus f plus f plus f plus f, because that's a counting number. So we're really dealing with here addition and subtraction. So 1 decimal place will give 1 decimal place, and that's why our answer would come out to be 68.2 degrees Fahrenheit. So I want to again point out that this is not the data that you'll be using in your lab report. This is just sample data to help you with these specific calculations. So I want to show you some tips for doing the post-lab calculations. For the first question, question 1, we're looking at converting grams into milligrams and kilograms. So you'll need a couple of bits of information here. You'll need the conversion factor for grams to kilograms. Also the conversion factor for grams to milligrams. And that's these ones here. So if you're going to go from grams into kilograms, to get the dimensional analysis right, we're going to have the grams cancel. So the grams will go on the bottom, kilograms will go on top. So it'll be 1 kilogram gives 1,000 grams. When we're talking about significant figures here, this has 5 significant figures, and we would be looking for our answer here to also have 5 significant figures as well. We're going to do the same thing on the other one here, so grams, and we're trying to get to milligrams. Milligrams will go on top, grams will go on the bottom. So it'll be 1,000 milligrams on top and 1 gram on the bottom. And again, we've got 5 significant figures here, and we expect to get 5 significant figures in our answer as well. Now keep in mind that trailing zeros, that is zeros in a number after that doesn't have a decimal point, will not be significant. So if you had something like this, let's say it was 129,000, that actually only has 3 significant figures. But if you had something like this, 129,000 and a dot at the end like this, then that would have 6 significant figures. So you've got to be a bit careful with that when you're doing your calculations. Alright, number 2. We're looking at 212 mils, and we're subtracting 71.8 mils. Now this is another significant figure issue, because we're going to come out, if you did this in your calculator, I think it comes out to be 140.2 in your calculator, but that hasn't got the correct number of significant figures. The number we need, see, this has 1 place past the decimal, and this has 0 places past the decimal. So our answer can only have 0 places past the decimal. So the question then becomes, is it going to be 140 mils or is it going to be 140 dot mils? Now I'm going to leave that to you to decide, because you've got to figure out which one is going to be more accurate. The clue I'll give you is this: if I've got 140, if you've got this number here, it's actually the result of rounding of a number between 135 and 144, whereas this is going to be a number that is going to be between 140.4 and 139.5. So I'll leave it to you to decide which of those would be the correct answer for number 2. Okay, to do number 3, I'm going to show some different data than what's here, but you'll use a similar strategy to what I'm going to show you here. So we've got 33.2 inches, we got 2.2 inches, and we've got 53.2 inches. So again, this is just different data. The first thing we're going to have to do is convert this into centimeters, because what we're looking for here is cubic centimeters. And the way we'll do that is we will use the conversion factor, 2.54 centimeters per inch. Now I want to point out that the 2.54 and the 1 here are counting numbers. They have infinite significant figures. So you'll get numbers out of those. Then you will multiply all those together. Now don't round them at this point here to the number of significant figures you want, because we're looking to multiply these together at the end anyway. And when we come up with something that is in cubic centimeters, we get 63675.67342. Now that's in cubic centimeters. Right, so that'd be centimeters, centimeters, and centimeters. And you know, this has not been rounded or anything, so I just used all these numbers as they were. And that's what I came up with in my calculator, but it hasn't got the correct number of significant figures. So what I'll do is I'll look at this and I'll say, well, that has 3 sig figs, this has 2 sig figs, and this has 3. Now my answer can't have any more sig figs than the least accurate number, which happens to be this one here, the one with 2 significant figures. So this needs to be converted down into 2 significant figures. Now if I'm going to do that, I'm going to have to use a strategy that involves doing something like this, or putting it into scientific notation. 6.4 times 10 to the 4th would be fine as well. The 3 zeros here are not significant because there's no decimal in the number, but you'll notice we had to do something to take it down from the 10 significant figures that we initially had down to the 2 significant figures that we wanted, and that's how we would do it, either in scientific notation or as a number that has trailing zeros that aren't significant.